Hi everyone, welcome to the second video. This is my second time recording this, unfortunately, because OBS screwed me over by not getting the whole screen for a lot of these recordings. So I have everything up on the screen right now, and I'll just try and hide some of the stuff later down so that not too much is given away. So before we get into the main content, I want to give a broad overview of what math is what math is in general. And there are two kind of parallel views, one that's a bit more austere and one that is more interesting and worthwhile. So in the first, our perspective on math is really this combination of axioms, the laws of logic, and definitions. And so axioms are these statements that we assume to be true. We can't just start from nothing, just start from no true statements and try to generate all the true statements that can be derived and just have this set of what is true. You just can't do that. So we have to assume certain things to be true. So for example, you guys should be familiar with Euclid's postulates for Euclidean geometry. That's an example of having this set of axioms from which you derive all of these statements that are true. And so whenever you guys did geometry, that's what you were doing. You started with this set of 5 axioms, and then from there, you did all these proofs to generate all these true statements about Euclidean geometry. Okay, so the question is, how do we actually take a set of established true statements and generate new true statements from that? And so this is where the laws of logic play their role. Laws of logic also are statements that we have to assume to be true, but they're relatively intuitive. So primarily they say that statements can only be true or false. So there's no third nebulous option. And they also cannot be both true and false. So essentially, statements can either be true or they can be false exclusively. And so this kind of gives us a sort of process of elimination kind of phenomenon where we eliminate contradictions, or we can show like direct implications and stuff like that. And that is what enables us to derive new true statements. And so those by themselves, just the axioms of that we assume to be true, and then the laws of logic, those are really enough to just give us our whole set of statements that we could derive in math. But what mathematicians always do is that they realize that there are these useful, repeated, like common concepts that show up in whatever work they're doing, and they say, well, hey, we should probably call this something, give it a definition, and study it more. So alongside this axioms and laws of logic, we introduce definitions into our fields of study, and that kind of gives us directions to go into. So when you're doing Euclidean geometry, there is nothing really fundamental about the ideas of certain shapes, like certain quadrilaterals and stuff like that. But you saw that they were useful, and they're common just shapes, or maybe interesting like special shapes with special properties that would come up, and you gave them definitions, and then you could prove stuff about them. And so these together, you could say, is sort of what all of math is. And that, to me, is pretty dry, because the idea is that you have this set of axioms, and then you have something like, oh, we have P is true, and then P implies Q, and then Q implies R, and R implies S, and you generate this whole tree of, derived true statements, and it's like, okay, I can follow along each step because it's just, logical steps. But you don't really gain a lot through that other than the sort of stated purpose of getting all the true statements that you possibly can. And so what happens in parallel that really makes math interesting and is really why everyone does math, no one does it for the former reason, is that you get this conceptual understanding just about the world and nature, either on like a physical level or a more sort of fundamental level, that I think you'll come to appreciate when we do more abstract math, and you'll see how like, oh, this is kind of different from just like the physical world in a sense. It's what Plato would call I guess the forms, I guess. This idea that there's this abstract truth that exists beyond the sort of physical realm, and not in a sort of supernatural way, but just the idea of like a mathematical forms, like a mathematical square exists as an independent concept from just like a square you could draw no matter how perfect it is. That's the kind of idea that I'm talking about. And then getting a conceptual understanding for things like that, and not just grinding through all of these logical steps and not really understanding what the hell is going on along the way. This is really the most important part, and that's what I hope to communicate to you, this conceptual understanding. Okay, so now getting back into our main stuff, I thought of some more inspired examples with all of these sort of statements that I was talking about last time. So I'm going to introduce the terminology for these because I think it's a bit clunky for me to just call this like for all and there exists. So this is called the universal quantifier when I say the for all, and this is called the existential quantifier. So we call them quantifiers because they're essentially telling us about the variable or the element that we're introducing into whatever work we're doing. So if we're doing a proof and we introduce x as a part of some set, it's an element of some set. And if we have this universal quantifier, we're saying that x can be an arbitrary element of that set. So in some sense, we're considering all the elements of that set. That's why it's universal. And if we're dealing with the existential quantifier, then we're just saying there exists some element of this set that satisfies this property. Okay, so the examples I have I've come up with are this idea with identity elements of certain sets. So sets with certain operations. So in particular, the real numbers, we can do addition and multiplication. And each operation has an identity element. What that means is that when we do this operation with some arbitrary element of the set with what we call the identity element, we get back that arbitrary element. So for multiplication, we have, for all x in the reals, x times 1 equals 1 times x, which is just equal to x. So 1 is what we would call the multiplicative identity for the real numbers, because if we multiply 1 with anything, we get back that same number. Then similarly for addition, if we say, we can say for all x in the reals, x plus 0 equals 0 plus x equals x. So hopefully you kind of see what's going on. The idea is that there is this one element that when we combine it in this operation with an arbitrary element of the set, it just acts as sort of giving the identity of that element. That's what we call the identity. Okay. And we could phrase it more abstractly in combination of quantifiers. So for this additive identity, we're basically saying that there exists an x in the reals such that for all y in the reals, x plus y is equal to y. So it just gives back y. And then for multiplication, we essentially say the same thing. There exists x in the reals such that for all y in the reals, x times y is equal to y. Okay. So I want to point out that there's a very, and I pointed this out last time, I think, as well, but there's a very important difference between having there exists and then for all, or having for all first and then there exists, right? The order of these quantifiers really matters. Because if we're saying for all y in the reals, there exists an x in the reals such that x plus y equals y, then what we're saying here is that we're going to fix y, that's a real number, first, and then consider the rest of this. So in the last video I talked about, we can read this universal quantifier as for all, or for every, or for each. And in this scenario, reading it as for each can be the most helpful. Because if you read it as for each y in the real numbers, there exists an x in the real numbers, then you can see that we're saying, oh, I'm finding an x in the real numbers that can depend on the y that I'm considering. And that's different from above, where we're saying there exists an x such that for all y something, is true. That means for this particular x, this proposition has to be true for all y. So one x will work for all y. Okay. So if you read through this, this is still true because this one is true. But, in general, we'll actually see that one will be true and one could be false. Okay. So coming down here, I think I promised in the last video I'd talk about how to negate statements with these quantifiers. And so if we're thinking about the proposition, just the one in the parentheses, for all x in A, p of x is true. So p of x is some proposition that could depend on what x is. So for one x, it could be true. For another x, it could be false. If you want to say that as a whole, this statement is not true, right? So I've added the negation. So let's think about when it is true. So for all x in A, p of x is true. That means that for every element of A, p will be true. Okay. As a whole, this is false. When? Right? That's the question. Well, if it's not true that for all elements of A, p is true, there has to be at least one element of A where it's false. Right? So that means that this is equivalent to saying there exists an x in A such that p of x is false. Okay, hope that makes sense. And then there's a similar idea for the next one. If we consider there exists an x in A such that p of x is true, and now I want to say that as a whole that's false, that means that there cannot be an x in A where p is true. That's what we're saying, right? Otherwise, there would exist an x in A where p is true. So if there cannot exist an x in A where p is true, the only alternative is that for every x in A, p is false. Because p can either be true or false, and that's it. So for all x in A, we have p is false. And so this is how we negate statements with these quantifiers. And so hopefully you see a bit of this pattern. When we negate the universal quantifier, it turns into an existential quantifier, right? So we have for all goes to there exists. And when we negate the existential one, it turns into a universal one, right? So there exists goes to for all. And then the proposition within here just becomes negated. So this is a sort of a simple calculational rule to negate these kind of statements. So I personally like to think through it still without just kind of, blindly going through it. But sometimes you have statements where there's a lot of these quantifiers in combination with each other, and it can take a lot of time to try and think through what should I write as that's equivalent to this. And so just using this kind of rule of flipping stuff, it can be pretty useful. Okay, so now let's move on to sets. So my first question that I want to ask you is, what should we consider as our sort of rule for saying that two sets are equivalent? Right? So we had this idea of sets being a collection of elements, and these elements are some abstract objects that, they could be numbers, they could be sets themselves, they could be really anything, right? But our main idea is that they're just collections of elements. So when are they the same? Well, we want to say that if they're the same, well, so if A equals B, right, A and B are the same sets, that all of the elements of A should be elements of B, right? There shouldn't be an element of A that is not an element of B, and yet somehow A and B are the same sets. So we would have this idea that if X is an element of A, then that should imply that X is an element of B. That way we're guaranteed that all the elements of A are then elements of B. And similarly, the same should be true in the opposite direction, right? If A equals B, B should be equal to A. That's part of being equal. So all the elements of B should then be elements of A. So we should have that if X is in B, that would imply that X is in A. Okay, so what this is saying then, if you look, we just have the structure of one proposition implying another, and then at the same time, we have the implication in the opposite direction, which means that we're saying that X is in A if and only if X is in B. And so if you're thinking, well, is this enough to say that they're equivalent sets? Let's think about this last statement a little bit. We know that if we have two propositions that are true if and only if the other one is true, then they're logically equivalent, right? So we're essentially saying that whatever sort of classification scheme we're using to put elements into A and then another one to put elements into B, they have to be logically equivalent, because when we put an element into A, it must also be put into B. So whatever classification schemes we're using then have to be equivalent. And so it makes sense to say that A and B are the same sets. Okay, so first of all, this is useful because we now have a definition of set equality. The second of all, what it lets us do is represent sets not just as essentially lists of their elements, but also through placing conditions or constraints to give information about the elements of the sets and basically tell us what they are. So for example, I could describe the set A as literally listing out all of the positive real numbers, right? So I may not actually physically write them down because that would be impossible, but I could sort of, conceive of a set where the elements I just see like they're all the positive real numbers. Maybe you could envision it by visualizing a real number line, and then it's just this sort of right half of it. Okay. Then I could describe the set B as this. Not literally all of these elements that are the positive real numbers, but just say that my elements of B are the set of real numbers, right, x and the reals, such that x is greater than 0. And so now, it may seem very intuitively obvious that these are the same, but the point is that just from their given presentation, they're not immediately the same. But we can pretty easily show that an element of A, where I just have literally all of the values, must be in B because it satisfies this condition. And then the other way around, if an element X satisfies this condition, well, then I can pick out the value from this sort of quote-unquote list that is in A. So this idea that A is equal to B if X is in A, if only if X is in B, it lets us represent sets in this very convenient, compact way. Okay, and this idea is called extensionality. It's it's kind of one of our axioms for saying that a set is equal to another set. Okay, our next idea is then that of a subset. And so I have given away what I'm going to talk about next, but I don't really have a choice. So if we want to talk about the idea of one set being a subset of another set, the main conceptual idea is that if A is a subset of B, we're saying that A is completely contained in B. That's what we're trying to describe and then formalize with these logical ideas. So I have a visual here. We have a set A, and then completely enveloping A, we have a larger set B, right? And so if A is completely contained in B, what we can see that we would not like to be true is if A somehow leaked out of B, right? If there were elements in A that were not in B. So if I somehow extended this out and then it just leaked out, then we wouldn't say that A is a subset of B, right? Because it's not contained in B. So what would not be true is if X is in A and also at the same time X is not in B, right? We wouldn't say A is a subset of B. So what must be true then for A to be a subset of B is that if X is in A, then this implies that X is in B. Excuse me. Right. And another way of representing that would be to say for all X in A, X is then in B. And these two are equivalent. These are equivalent definitions for saying that A is a subset of B. So this is how we would define A as a subset of B. We write it as A and then this symbol B. It's like a sideways U. The side that is kind of open, right, that has the two ends, is talking about the larger set. And then this is true if X in A implies X in B. Okay. If you're wondering what this line here is for, this is saying that we're leaving open the possibility that A is equal to B. Because even though A is completely contained in B, we're not necessarily saying that A is smaller than B, or that there's an element of B that is not an element of A. Many times that will be the case, but in many contexts, we're okay with saying that A could be equal to B, because we'll be proving some statements that talk about a subset of some, larger space, but that theorem might also be true for the whole space itself. So there's no reason to exclude it. And other times that's not the case. Sometimes we do need to exclude it. So when that is the case, we'll be leaving out this line. But there is some convention where some people just don't put the line at all, so it's something that, overall in your life you need to watch out for. Okay. So one thing to note then, one last thing, is that if we go back to our idea of what it means for sets to be equal, we said that A is equal to B if X in A implies X in B, and X in B implies X in A. Well, if you think for a bit, and maybe pause if you want to, and we look closely, this looks an awful lot like the definition for A being a subset of B. And this looks an awful lot like the definition for B being a subset of A. So if we just substitute in A is a subset of B here, and B is a subset of A here, then we'll see that, and with a little work showing the other direction, our first theorem, which is that a set A is equal to a set B if and only if A is a subset of B and B is a subset of A. And so this is really important because this is one of our most common, like just typical strategies for proving that two sets are equal. And that in itself is very important because if we are dealing with this set A that is in its own mathematical context, it might be just something related to, let's say, like geometry, right? So geometry may be in what you're familiar with, but also there's a more modern notion of geometry which deals a lot with calculus and other kind of structures like manifolds and stuff like that. And maybe we're talking about a different set B that's related to more algebraic context. So that's stuff really to do with like certain sets and operations between them or something like that. And if we somehow show that these two sets are really equal, or there's some sort of equivalence correspondence between them, then we're not just showing that, but what we're showing is this conceptual link between two different areas of math. And that is the actual important part. So showing that these two sets are equal really serves to construct a connection between just two different areas of math, and that will reveal some just something amazing about nature and like how the world works, that this connection exists. So in some sense, like if you have done that, you've discovered something new about the world. And usually that sort of conceptual understanding, when you're proving it, lies in proving one of these statements, that A is a subset of B or B is a subset of A. One of these is usually obvious. Sometimes both are not obvious, but usually one will be obvious and the other one will actually provide some conceptual insight. So there's that. This can actually have really profound implications. It depends on the context. So in the next video, we'll be talking about unions and intersections. And I will also have to redo that one, unfortunately. But it should not be as bad. But yeah, I'll see you guys in the next one.